This is our next to the last lesson in our unit on transformations, and today we're going to talk about symmetry. We're going to talk about three kinds of symmetry, the first one being line symmetry or reflectional symmetry. A figure has line symmetry if there's a reflection for which the figure is its own image. In other words, if you reflect it and it ends up right on itself, it's got line symmetry. The line of reflection is called a line of symmetry. And here's an example. Look at this isosceles trapezoid. See this line of reflection or line of symmetry? If I fold that trapezoid on that line, then the left half will be right on top of the right half. Okay, so an isosceles trapezoid has line symmetry. Now we're going to talk about rotational symmetry. A figure has rotational symmetry if there's a rotation of 180 degrees or less for which the figure is its own image. For example, look at this equilateral triangle. If I were to rotate this 120 degrees, then the pre-image would be the image. It maps onto itself with a rotation of 120 degrees. There's not a rotation less than that, a smaller number of degrees I could rotate it. I could rotate it 240 degrees, right, and then 360 degrees. So if there's a rotation of 180 degrees or less for which the figure is its own image, it has rotational symmetry. So what do you think? How about all of the regular polygons? You think they'll all have rotational symmetry? Good question. The angle of rotation for rotational symmetry is the smallest angle needed for the figure to rotate onto itself. And remember, if the angle needed is larger than 180 degrees, then we don't say that it has rotational symmetry. It has to be between 0 and 180. Okay, so let's look at this little image of the sun here. What's the angle of rotation for the figure above? Well, I can see that if I kind of think about this, turn it one click, it's going to rotate onto itself. But what is the measure of that angle? Well, let's do this. Okay, if I rotate it this much, that's 90 degrees, right? But it's really half that I have to rotate it to get it to map onto itself. So its angle of rotation is 45 degrees. Guess that actually goes right there. Okay, rotational symmetry. Now, a figure with 180 degree rotational symmetry also has what we call point symmetry. So for example, look at this parallelogram here. If I rotate this thing 180 degrees, then it's going to map onto itself right. If I rotate this in 180 degrees, it'll map onto itself. So to have point symmetry, a figure has to to have point symmetry, a figure has to have rotational symmetry, and it has to be 180 degrees rotational symmetry. Okay, each segment joining a point and its 180 degrees rotation image passes through the center of rotation. So the center of rotation here is the center of the figure. Okay, so let's do some examples to see what we know. Determine if the figures below have symmetry and indicate which kind if they do. If the figure has rotational symmetry, what is the angle of rotation? All right, let's think. Does this have line symmetry? Sure it does. Here's a line of symmetry, right? That might not be the only line of symmetry. I suspect it isn't. But anyway, it definitely has line symmetry. How about point symmetry? Remember, to have point symmetry, I got to have rotational symmetry. So let's decide if we got rotational symmetry first. If I rotate this thing any amount of degrees from 0 to 180, is it going to map onto itself? Sure it is. Okay, now, if it has 180-degree rotational symmetry, since it does have rotational symmetry, it has point symmetry. Well, if I were to rotate this 180 degrees, it's definitely going to map right onto itself. So it definitely has point symmetry. And so it tells us if we have rotational symmetry, what is the angle of rotation? And remember, the angle of rotation is the smallest angle that we can rotate this figure for which it'll map onto itself. So how many degrees will I have to rotate this before it maps onto itself? Well, that's just going to be its central angle, right? It's going to be its central angle. So this regular hexagon has a rotational symmetry of 60 degrees. Okay, how about the equilateral triangle? Is it going to have line symmetry? Sure it is. Sure it is. Right there's the line of symmetry. So I got line symmetry. Let's check rotational symmetry. Actually, we had that for the example on the previous page, but we know that it does have rotational symmetry. If I rotate it 120 degrees, it maps onto itself. So how about point symmetry? Remember, point symmetry exists if you have 180-degree rotational symmetry. Do I have 180-degree rotational symmetry? No, I don't, because if I rotated this 180 degrees, what I would have would be the upside down triangle. So we don't have point symmetry here. We just have line and rotational symmetry. How about this parallelogram? It's not really marked, but we have to do that to show that it's a parallelogram. Okay, line symmetry. Do we have line symmetry? Actually, we don't. There's no line that I can draw through this parallelogram for which if I fold it, the image is going to map onto itself. You might be tempted to think that this would be a line of symmetry, but actually, if you folded this parallelogram along that line, this top point up here would end up down here somewhere. So we don't have line symmetry. So let me just erase that line. We don't have line symmetry. Do we have rotational symmetry? Well, yes, we do. If we rotate this thing 180 degrees, then it's going to map onto itself. So we do have rotational symmetry. It's 180 degree, which tells us we definitely have point symmetry. Okay, how about this right triangle here? Do we have line symmetry? This is a scalene triangle, by the way. All the side lengths are different. We don't have line symmetry. We don't have point symmetry. We definitely don't have rotational symmetry. So what we do have is no kind of symmetry. No symmetry there for that scalene right triangle. Okay, oh, here's one more. Here's one more. We got the little star. Let's think about it this way. What if I draw these sides in here? Turns into a regular pentagon, doesn't it? So do I have some line symmetry here? I sure do, because look at this. There's a line of symmetry, right? So I got line symmetry. How about rotational symmetry? I believe so. I think if I rotate this many degrees, then this thing is going to map right onto itself. How do I know how many degrees that is? Oh, well, it's just the central angle of the pentagon. What's the central angle measure of the pentagon? 72 degrees. 360 divided by 5. So I got rotational symmetry. How about point symmetry? Nope, no point symmetry, right? Because if I rotate this thing 180 degrees, then the point is going to be down here. It's going to be upside down then. Okay, let's see what we got here. Sketch the graph of each equation and describe its symmetry. You know what? I'm going to actually save these for you to do. I want you to graph all these on the little grids I've provided and then tell me what kind of symmetry each one of these figures has. So I want you to pause right here. I want you to do these, and actually I'm not going to put the solutions up because I want you, it's been a while probably since you've seen a graph of this. I want you to graph it yourself. If you're thinking, I don't know how to graph that, well, guess what? Make a table. Make a table to graph it. You can do the same here. All right, you could do the same. This is absolute value of x, right? Hopefully you haven't forgotten about the absolute value. Absolute value. Make a table. This one here, what is this? We studied these just a little while back. So I want you to do these, and then we'll talk about them in class next time.